Disclaimer before we start the lesson. This video is going to be boring, okay? Because we are just going to prove that this formula is true. So if you are that kind of person who is given a formula which is said to be true and you believe it straight away, you can skip this video, okay? We are going to use this formula to prove some vector identities in the next lesson. But if you want to see why this formula works, this is your video, okay? So it's longer than I expected, much longer, but I mean, it's just to prove that this formula is indeed true. So let's go with the video. Welcome again, Vitas, to a new lesson of this course. So you might wonder, why are we still in lesson 1.1.2? And the reason is that we need to see some properties of the Levi-Civita symbol, and I swear this is the last part of this lesson, okay? So we are going to see this property. We are going to multiply two Levi-Civita symbols together and contract their last indices. And this is going to be this strange combination of kronecker deltas. So we are going to demonstrate why this is true. And first of all, let's recall Einstein's summation convention. Well, of course, as I have said in the previous lessons, all the indices are going to run from 1 to 3, okay? Because we are working in 3 dimensions. And we are going to expand out the sum, so we are going to get 3 terms, which is going to be k going from 1 to 3. So let me write this just a second. Okay. So we can think of this object as another object which has 4 free indices, because you might notice that we have 6 indices, but 2 of them are contracted together, so the k's are dummy indices, and we have 4 free indices. We have I, j, m, and n. So this is going to be like an object which has 4 indices, and depending on the values of those indices, it's going to be one value or another value. Okay, so we are just calculating the components of this strange object of 4 indices. So first of all, notice that we are only going to work with the indices I and j because this formula is symmetric. So we could also write mnk ijk. Okay, we could swap the two Levi-Civitas in the multiplication, and it will be the same. So instead of demonstrating first varying the ij indices and then for the mn indices, if we do the demonstration for the ij indices, then it's going to be also true for the mn indices, as we can swap the both Levi-Civitas. So we're going to start. We're going to suppose that I and j are equal, okay? So we're going to call this index, for example, L, and I'm going to write a star. So why the star? We're going to do like a notation, which is that, imagine, for example, that we have an object with 2 indices, and we want to write a component whose indices are equal, but we don't want to sum, okay? Because if we write tii, for the Einstein summation convention, it's understood that we are summing, and this is t11 plus t22 plus t33. But in this case, we don't want to sum our indices. Imagine that you just want to write a component who has the same indices, but it's not summing. So we will just write I star, I start. And by writing the stars, like we are saying that we don't want to sum those indices, okay? So whenever we have 2 repeated indices, but they have a star, the Einstein summation convention doesn't apply, okay? So this is not a sum of components. This is just a component which has the same 2 indices, okay? So let's check if this formula works for these both indices being equal. And we have that epsilon L star k times epsilon mn k is going to be delta L star m delta L star n minus L star n L star m. So we know by the property of the Levi-Civita symbol that if we have two repeat indices, it's going to be 0. So this left hand side is going to be 0. And for the right hand side, we can see that we can swap these deltas, okay, because multiplication is commutative, and this is also going to be 0. So we see that in fact, if the two indices are equal, the formula applies. So we can check now, for example, that we saw in the previous lesson that the Levi-Civita symbol was completely antisymmetric. So this means that, in theory, if we swap any two indices, let's say j and I, there is going to appear a minus sign. So we are going to check that property, okay? We are going to swap these indices, and we are going to write well, the same formula, which is this one, and now we are going to write it with the swap indices. So this is going to be just this expression, and we can pull a minus sign from these terms, and we will have delta im, delta jn. This is this term, and I have swapped these deltas, and now we're going to write the other term, which turns out to have a minus sign because minus times minus is plus, and it's going to be delta in times delta jm. And you can see that what we have here is exactly this thing, and this thing is this other one. So we are going to write minus aijk times amnk. So we have proof that if we interchange these indices, there is going to appear a minus sign. And as we have said before, this also is a demonstration for the mn indices, because we could swap these Levi-Civita symbols, and the same proof would apply for this situation. So we have demonstrated the cases for both indices being equal and interchanging the indices. And we don't need to prove more things for the indices mn, so we just have to demonstrate the formula for the ij indices. So we are going to have three possibilities for I and j. I equals 1, j equals 2, I equals 1, j equals 3, and I equals 2, j equals 3. These possibilities have been covered right here, and if they are equal, they have been covered right here. So, and you might ask what happens for the m and n, and we'll see what happens for those indices. And if we want to do the opposite situation, first mn and then ij, as I have said previously, it's the same thing, okay? So let me copy this real quick, and we're going to start for the three cases. Okay, so I equals 1, we are going to have these terms, and we can see that this is going to be 0 because here we have two repeated indices. So we are going to be left just with these two terms, and we are going to make this case to be, for example, j equals 2. So if we make j equals 2, what we are going to have now is that we are going to have 1, 2, 2, and here 1, 2, 3. So now we have here, I'm sorry, here's a 2. So we are going to have also this term is going to vanish, and we are going to be left only with this term. This is an even permutation, so it's going to be 1, and this is just epsilon mn3. And we have to check for the formula that this is indeed delta 1n delta 2n minus delta 1n delta 2n, because recall that this is in theory im jn minus in jm. So this is very easy to check, because if m or n is equal to 3, okay, m or n equals 3, this is going to be 0, so we are going to have 0 equal, and now we have to check that this will be 0, but this is very easy, because if any of them is 3, let's say the index m is 3, so this is going to be 3, we have 1, 3 different indices, this is going to be 0, and here 2, 3 different indices, this is also going to be 0. So the formula for this case is correct. Now we are going to see what happens when m equals 1 and n equals 2. And now we are going to have epsilon 1, 2, 3 equals delta 1, 1 delta 2, 2 minus delta 1, 2 delta 2, 1. So evidently this term is going to vanish, and now here we have delta with repeat indices, which is 1, and also delta with repeat indices, which is also 1. Thus this is going to be only 1. So you might want to check m equals 2, n equals 1, but as we said previously, we saw that for ij, if we swap them, there is going to be a minus sign that is going to change, and this also happens for mn, because we can just swap these factors, and the proof that we made here for I and j is going to work also for m and n. And you also can apply this to the case that you imagine what happens if m and n equals 1, both of them, or 2, and if they are equal, we show that it's going to be 0 equals 0, so it's also going to apply. So we just need to check this case, and we know that for this one we are going to have epsilon 2, 1, 3, and it's going to be minus 1. Now we are going to check I equals 1 and j equals 3, and in this case we're going to have epsilon 1, 3, 1 times epsilon mn1 plus epsilon 1, 3, 2 epsilon mn2 plus epsilon 1, 3, 3 epsilon mn3, and this is just delta 1m delta 3n minus delta 1n delta 3m. We can see that we have here repeated indices, so this term is going to vanish, and also here we have 2 repeated indices, so this is going to vanish, and we are only left with this. So in this term we have epsilon of 132. 132 is just an odd permutation, so this is going to be minus 1, and thus we are going to have that minus epsilon mn2 is going to be these deltas. So we are going to check if this is true. Let's say that m or n is equal to 2. So in this case, evidently, this is going to be just 0. And now you can see that if we write a 2 here, let's say that m equals 2, okay? So this is going to be 1, 2, so this is going to be 0, and this term is going to vanish. And the same for this 1, 3, 2, different indices is going to vanish. And if you imagine this for n, it also works, because different indices 0, and here different indices is 0. So this is true. And now we are going to have, for example, m equals 1 and n equals 3. So in this case we have minus epsilon 132 equals delta 13 delta 33 minus delta 13 delta 31. So you can see that this is going I'm sorry, I'm going to check. Okay, sorry, this is a 1. Okay, this index is an m, and m equals 1. So here we have a delta which equals 1, another delta which equals 1, and these are different indices, so this term is going to vanish, and this is just going to be 1. And we can see that this is true because epsilon 132, 132 is an odd permutation, so this is going to be minus 1, and minus 1 times minus 1 is just plus 1. So for this case of m equals 1 and n equals 3, the formula works. And as we said previously here, we can swap the roles of m and n, and this will still hold. So we are left just with one combination of I and j, which is I equals 2, j equals 3. It's all the same thing. So let's say that m or n equals 1. Well, we need to write first the Levi-Civita summation. And it's going to be, let me copy this so that we can write it faster. It's going to be 2 and 3, also 2 and 3, and also 2 and 3, and here there was a 3. So two repeated indices, this term vanishes, two repeated indices, this term also vanishes. And this is going to be equal to this combination of deltas, 2m 3n minus 2n 3m. And we are going to be left with just, let me write this, well no. Well, of course, this is an even permutation, so this is going to be 1, so this we can omit this factor, and it's going to be the equality, basically that epsilon mn1 is going to be delta 2m delta 3n minus delta 2n delta 3n. I'm running out of space, but I hope, well, it's all the same. So now if m or n equals 1, we see here that we are going to have repeated indices everywhere, so this is all going to vanish. And if m or n is a 1, this is a repeat index, so this is also going to vanish. So we have again the 0 equals 0, this is true. And now we are going to check m equals 2 and j equals 3. I'm sorry, m equals 2 and n equals 3. So in this case we are going to have, let me see, epsilon 231 equals delta 22 delta 33 minus delta 23 delta 32. So different indices is going to vanish, same indices, this is 1, same indices, this is also 1, so this is just going to be 1 for the right hand side, and for the left hand side, so 231 we read to the right, so this is an even permutation, thus this is going to be also 1. And as before, this also serves as a demonstration for the if we interchange both indices. So we have finally checked all the components. This was a long journey, but we can firmly say that this equation is indeed true. So this equation is very important because in the next lesson we are going to use it for deriving some vector calculus formulas, and it's important to know where it comes from and to check that it actually works.